Hello, welcome to On Wildlife. I'm your host, Alex Ray. On this podcast, we bring the wild to you. We take you on a journey into the life of a different animal every week, and I guarantee you you're going to come out of here knowing more about your favorite animal than you did before. We're changing things up a little bit this week and next week because we're going to be talking about some animals who haven't been around for a little while. Actually, they haven't been around for millions of years. I got to interview Dr. Paul Selden, a paleontologist and professor at the University of Kansas. So let's hop in our time machine to go back a couple 100 million years to learn about prehistoric arthropods. When you think about fossils, you think about huge dinosaur bones like the T-Rex or the Triceratops, but there's a lot more to paleontology than just that. Today, we're going to talk about fossil arthropods, which come in all shapes and sizes. You may be wondering what arthropods are and if they're still around today, and the answer is yes. An arthropod is an extremely broad category that encompasses insects, spiders, scorpions, and even crustaceans like crabs. And arthropods have been around for much longer than even the dinosaurs. They date back all the way to 500 million years ago. And they're also Paul's specialty, and he really focuses on fossilized spiders. He's written multiple books on paleontology and has been doing this for longer than I've been alive, so you know he's got some really cool stuff to say. And if you know me, you know that I'm always going to try to bring it back to the conservation of today's species, which Paul is going to give us some more insight into as well. All right, let's take a quick break, and then you'll hear my interview with Paul. The person that I'm going to recognize on today's episode of Notable Figures in Science is Dr. Harold Amos, a microbiologist who lived from 1918 to 2003. After serving in France in World War II, he graduated with his PhD from Harvard Medical School. After graduating, he taught for multiple years and eventually became the department chair for the medical school. This made him the first black man to become a chairman at Harvard in the medical department. During his time there, he published over 70 different scientific papers, mostly on bacteria, and he's given us a lot of the information that we know about today regarding bacteria. Aside from also being an advisor for the Nixon administration, he was one of the founding members of the Harold Amos Medical Faculty Program, which helped give people of color better opportunities to become faculty members at Harvard. He achieved many milestones in his life, which is why it's so important to recognize him. If you want to learn more about Dr. Amos or this series, you can visit onwildlife.org. Okay, we're back. Enjoy the interview. Hi, Paul. Thank you so much for coming on the podcast today.
You're welcome. It's nice to be invited and glad to be able to help.
I'm glad, and I'm really excited to get into talking about arthropods today. So first, can you just tell us a little bit about yourself and how you became interested in paleontology?
Yeah. Well, I suppose I started off being interested in natural history, in animals as a kid. I watched birds and collected butterflies and moths, made a collection of those. But I also got interested. I had a very good geography teacher at school who got us interested in the landscape, and geology and that kind of thing. So when I was choosing a subject to do at university, it really had to be a double honors, on geology. I did geology and zoology. Oh, wow. So combining animals with geology. And I wasn't particularly interested in fossils, but that's naturally how those two subjects come together. Uh-huh. So by the time I got my degree, I was, well and truly, and we had some excellent teachers in the university who were, got you fired up about collecting fossils. Yeah.
That's awesome. And I always think that good education starts with a good teacher. If you could get the kids interested in what they want to learn, then you can teach them anything, I think.
Absolutely. And it's so much easier if you can go out and actually find stuff. At the moment, we're all stuck here, unable to do very much. But if you can get out there and find things, make a collection, you know, um, and you really learn much better that way than through books and TV and so forth.
Oh, absolutely. And going off of that, so have you dug for fossils in the field yourself?
Well, I mean, apart from doing it as an undergraduate and also teaching it in university, where you take students and show it to them, I mean, the actual digging process is something that the public always imagine that paleontologists do. Well, it's true for things like dinosaurs, because you find a bit of a dinosaur, then you go back with a team and you spend days and days digging. But the fossils that I study are actually extremely rare. And if I were to spend all my time digging for them, I'd never find one. So I rely on very keen amateur people, mostly, who spend their weekends digging and collecting everything. And then, my particular interest is fossil spiders and things like that, arachnids, which are extremely rare. But one in every, out of a place that's, say, rich in insects, maybe one in every 10,000 is a spider.
Uh-huh.
So, as I say, they're very rare. But once they're found, they make their way to the museum, hopefully, and then they say, "Hey, we've got this fossil spider. Come and study it." And that's when I go to the museum and borrow it or study it there. But I like to go and visit where it came from to get a feeling for the whole. How it relates to everything else in that rock strata.
Oh, that's so cool. And how can you, let's say you just like stumble upon a fossil. How do you tell that small of a fossil from just a regular rock?
Oh, well, yeah. I mean, you learn eventually. I get sent a lot of sort of oddly shaped pictures of oddly shaped stones. For people who think, well, I think this looks like a bird's head or an egg, or a bit of dinosaur tooth or something. Well, generally, the fossil isn't the shaped rock; it's within the rock. So normally, you find it embedded in rock, and you see a pattern, and you get used to the patterns. So, I mean, an ammonite, a curly whirly thing, becomes fairly obvious after a while.
Ammonites were shelled creatures that lived over 200 million years ago.
Seashells of any kind are kind of obvious, but often you see them in cross section. So you have to do a bit of three-dimensional thinking to imagine what you're actually looking at, and it certainly does take some practice.
Yeah, absolutely. That's really awesome. And so you were talking a little bit about how when you're actually looking for those big dinosaurs, it's very different from spiders and arthropods. So how does the study of fossil arthropods different from other areas of paleontology?
Well, it's not different generally, but it's each particular group of animals has its own way of being studied. If you're simply interested in the fossil itself, then you just take it back to the lab, and that's where you can start preparing it. And how you prepare it depends on how it's preserved. So it's very important to know how it's preserved. If it's in amber, for example, then you have to polish the amber in a particular way and get the light just right. If it's squashed in rock, you can sometimes pick out where the rock's still covering it in places. And the fact that it's squashed means you have to sort of try and imagine it three-dimensionally, whereas in amber, for example, it is three-dimensional.
Uh-huh.
Yeah, so there's so many factors come into play. You have to know what you're actually looking at, whether it's the actual skin or the shell, or whether sometimes it gets replaced by some other mineral, and all of those factors define how you interpret it.
Yeah, definitely. I cannot even imagine how hard it must be to find one of these fossils, because fossils are rare in general. Very few organisms ever are made into fossils.
Mm.
So the organisms that you're studying could get caught in amber. Could you just talk a little bit about what that means?
Well, something that's trapped in amber is a rather specific type of preservation. Amber is fossilized tree resin. So some trees exude resin as a result of damage, or there's a variety of reasons, and some trees do it much more than others. But it has a rather sweet, sticky sort of smell to it, and it attracts insects for some reason. I don't know why, but they get attracted to it. They then get covered in it, and a struggling insect will attract, a lizard or a spider or something that thinks it can capture it, and then they get caught. And so it's rather specific. I mean, it really samples things that live around tree trunks, obviously. Eventually, when the forest dies and the amber sort of floats away and gets deposited in mud, and you can find it, by digging up the mud, or even walking along the seashore where it gets washed up.
And that's really amazing. And I don't know if you've ever seen Jurassic Park, but that's how they extracted that DNA. But I don't think that's really realistic.
No, but like all good science fiction, there's a grain of truth that they kind of built on.
Absolutely. So how do you determine how old a fossil is?
Okay, well, you really can't date the fossil itself normally, unless it's very, very young. I mean, if it's something like a tree that's died, say, 10,000 years ago, you could probably use carbon dating on it.
Carbon dating is one of the ways that we can use chemistry to figure out the age of something. We know exactly what carbon's half-life is, which is basically how long it takes for half of a carbon sample to decay. It's pretty complicated, but because we know carbon's half-life, we can test the fossil's chemical composition and figure out how old it is.
But for a true fossil, something that's like millions of years old, where the carbon's no good, what you have to do is look at the layer of rock that it's in. Now, we have throughout the world, we have a sequence of rocks that have been studied all over the world to give us a generalized geological column. The study of that is called stratigraphy, where you're looking at the strata. And we know if you find a trilobite, for example, you've got to be in the Paleozoic, because they became extinct at the end of the Paleozoic. If you find a dinosaur or an ammonite, you've got to be in the Mesozoic, because they didn't evolve until the end of the Triassic and died out at the end of the Cretaceous. Well, if you sort of continue that process down to individual species, certain species only lasted for a certain length of time. So you can build up a chronology of what is younger than or older than, and a whole sequence of events. But in terms of actually putting dates on it, you then have to use radioisotopes. And that's where, within this generalized geological column, there are certain horizons that will have things like, say, a volcanic ash. So when a volcano erupts, it's an instantaneous thing that is fixed in time. And you can study the minerals in there, and those minerals will have a ratio of parent and daughter isotopes that you can use a bit of calculation to work out the precise age in millions of years. And so a number of these horizons have been determined throughout the whole geological column. So you could very rarely say, well, this is exactly 63.752 million years old. You can normally say, well, it's somewhere between 63 and 64 million years old, which is good enough.
Yeah. And it's really insane how we're able to do this, and that we can even get those dates. Like, not it doesn't really matter that it's 64, maybe 63, but still, if we can get it in that time range, it's amazing that we can do that.
Well, I consider it's a bit like when you study history. I mean, the exact date, I don't think is quite so important as imagining everything else that was going on around at the same time. You know, what battles were going on, what kings and queens were around, what presidents were, you know, what other things were happening. You build up a whole picture. So if you say to me, oh, that's Pennsylvanian in age, I have a picture of these big forests of trees and giant dragonflies and stuff, you know, and that's an immediate picture. If you say it's 360 million years old, I have to scratch my head and work out, well, when was that exactly then?
Yeah, and that kind of brings me into my next question, which is, what can you tell about an ecosystem by looking at the fossils and the area around those fossils?
Well, there's actually more than just the fossils that will tell you a lot about the ecosystem, because it's the rock that they're in as well that's important. So, for example, if you look at a limestone, limestones are normally made in that they originate in warm, shallow seas. They're actually made of the remains of little animals, plankton that were living there, and other things, corals maybe. So you start, as you look at the limestone, you find corals and things. You find maybe some fish or something, you know, and you begin to build up a picture. And you compare two things. You're comparing the different kinds of animals and plants that were there, and comparing them to the present day. So there's something that we say in geology, that the present is the key to the past. So you've got to understand, for example, what a coral reef looks like in order to interpret a fossil coral reef. So a modern coral reef, we call it a coral reef. In fact, it's mostly algae, but you see a lot of corals there, and mollusks and fish and one thing and another. If you look at a fossil coral reef, you may well find it's dominated by sponges rather than corals, for example, but you can still gain an insight by comparing with the present day. And also the actual, as I said, the rock it's in. I've mentioned limestone. Say it's a sandstone. Well, now sand is being produced today, you know, in rivers and in deltas. It doesn't go far out to sea because it's too heavy. Once the river drops its speed at a delta, it drops that sand. So another place sand is formed is in deserts, but that's a different kind of sand. Mm-hmm. So, I mean, you can immediately get an idea, okay, I'm dealing with the river sand, or I'm dealing with the desert sand. Then you start looking at the fossils, and the desert sand may well have dinosaur footprints, say, because it's formed on land. The river sand may well have fish or, you know, mollusks in it. So you don't just use the fossils, because as you've already said, a great many things never get preserved. You know, soft things, worms, don't get preserved. So you have to sort of interpret the total environment, then imagine there probably were worms there. Otherwise, what would the fish be eating? You know? Yeah. So you gradually build up a total ecology based on what you've got, and then what you kind of infer was probably there, even though you may not have direct evidence for it.
Absolutely. And that really just shows how paleontology isn't just looking at fossils. You need the context of present day. You need the context of all the rocks. It's really complex and amazing.
It's quite a broad. I mean, something that's following on from that is that there are things called trace fossils, which I've kind of mentioned already. I mean, a dinosaur footprint is not a dinosaur. So it tells you that a dinosaur was there, and it kind of tells you what it was doing. You know, it was walking, right?
Yeah.
You may not get worms, but you might have worm burrows. So it tells you that the worms could live in the in the sand, so the sand had oxygen. It wasn't a horrible black, sort of putrid sand. It was a nice clean sand. So the two go together. You can make interpretations, even if you don't actually have the fossil there.
Yeah, and you talked about trace fossils a little bit with larger dinosaurs. Is there anything that you use to determine the behavior of smaller, like spiders and arthropods and other insects?
Yeah, you can see tracks of things like, for example, the Coconino Sandstone, which is just below the rim of the Grand Canyon, contains a lot of scorpion tracks. And we know they're scorpion tracks. You count the number of legs. You can see the occasional drag of the tail. It's a desert sand, and so we can interpret them as scorpions. So it doesn't tell us what kind of scorpion it is, but it does tell us that they were there and what they were doing.
That's really cool. And I think a lot of people are wondering what they looked like back then. So have you noticed any huge changes in the morphology of arthropods from then to now?
Well, the real answer is no. I mean, first of all, if you find a fossil scorpion, it's a scorpion because it looks like a scorpion. So it's no different. What we tend not to find is something that's half scorpion, half spider, because clearly such a thing never existed. But just occasionally, you do find a sort of missing link. I mean, when Archaeopteryx was first discovered, it was here was what looked like a little dinosaur, but it had feathers on. Okay, so that's kind of different, but it wasn't unexpected.
Archaeopteryx looks like a mix between a bird and a dinosaur, and scientists call it a transition species because it's evidence of the evolution from dinosaurs to birds.
And similarly, in recent years, we've discovered some rather curious sort of proto-spiders, which are clearly very spider-like, but have tails. Now, no living spider has a tail, but some of their relatives do. So, and these aren't particularly old. I mean, they're simply things that we sort of thought might be there because we've got the spider and then we've got its next nearest relative and there's nothing much in between. Mm-hmm. So when something like this pops up, you think, wow. But they live for an awful long time. And for all we know, they might even still exist somewhere in the deep jungles where we've never explored.
Yeah, definitely. And there's a lot that we haven't explored about our own Earth. So that would be really cool if they were out there. So what's one of the most interesting things that you've found during your research?
Oh, well, I suppose these sort of missing link things are probably the most interesting because it kind of started when we were studying fragments from rocks from Devonian age. Now, we're talking 400 million years ago now. And these are rocks, they're shales, so they compress things absolutely flat. But there's some up in New York State which were being studied by paleobotanists because they contain some of the oldest trees that we know about. But you can tell a lot by taking these shales and dissolving them. And you could dissolve shale in hydrofluoric acid, which is a horrible thing. It dissolves rock, but it leaves behind organic matter. And so you get little flakes, you get spores, plant spores, and you get bits of stem and stuff. But in amongst them, there are little animals. But a lot of these little animals, very few of them were complete. They were mostly fragments. So you'd get a leg and a head and bits and pieces. And so we were trying to put together the whole animal. It's like if, say, you have a jigsaw puzzle and you've only got half the pieces and you haven't got the box lid, right? So you're trying to put these things together. And just occasionally you get it wrong, And there were some sort of sort of whip-like pieces that looked like they had the right pattern to go with these spiders, but we couldn't fit them on anywhere, so we just ignored them, more or less. And it was later on that I found that a spider turned up in Russia. It came from a place called Perm, which is what the Permian period is named after. And it looked exactly like a primitive spider, like you find living today in Southeast Asia, but it seemed to have a tail. And we thought, well, it can't be a tail because spiders don't have tails. Well, anyway, eventually, long story short, we found some of these fragments from the Devonian with the actual tail attached to the body. So that, we were wrong in assuming spiders don't have tails, because there were some there back in the past that did. And we now know that they did, and we've even found them in the Cretaceous in the amber from Myanmar.
That's so amazing and interesting. It makes you wonder how they lost tails and why no spiders have tails today.
Yeah. Well, it's that this group was obviously successful for millions of years, but modern spiders went a different way and became extremely successful.
Yeah, definitely. And so does studying the fossils of arthropods give us any information about arthropods today and their conservation? Because I know you were talking about how we have to use what we know today to figure out what was happening back then. So can it go the other way around?
It can do. I mean, you can look at the thing about paleontology and geology is you've got the dimension of time, of a long time. So whereas today you might have been studying a forest for 50 years. I mean, the geological record will give you the record of a forest over millions of years or tens of thousands of years. And so you can track things, hopefully then it can be predictive. You can say, okay, well, this forest died out because, if you can find the factors that caused it to die out, then that will be predictive to be able to say, well, okay, if this forest is subjected to too much of this or too little of that in the future, then this is what might happen to it, because we've seen the evidence of what happened in the past.
Yeah, absolutely. And we've seen extinction events happen, and sometimes we know what caused them. And obviously, we can't stop a meteor from hitting the Earth, but we could stop some other things that could be preventable. So is there any way that the average person can support your research or the field of paleontology in general?
There's various ways. I mean, one way is to become interested in it, is to go out on, if you can get out on a trip and look at fossils, if you can go to a museum. I mean, museums are fantastic, and the more you know before you go, then the more you get from a museum collection. And I mean, they exist to tell you about paleontology, and of course, museums, are ranked according to the number of visitors they get, so it helps them if you go. And there are these kind of crowdfunding sites now, which I know some of my students have been involved with, where you can, you put so much money in, and it helps a young student, who's, say, going out, wants to go and collect fossils somewhere, and in return you kind of get bulletins of what they found. And I mean, the thing is, if you find a fossil that's new and you donate it to a museum, the researcher will study it, and then they'll nearly always name it after you. So if you want that kind of thing, then that's always, that if you find interesting fossils, there's always that sort of, and so fossils must go to museums. And unfortunately nowadays there's a lot more trade in fossils, and so a lot of fossils command high prices that museums can't afford, you know. And so, if you want, say, to collect, I don't know, amber fossils, make a good collection, and then donate it to a museum, then, you'll get remembered by having the collection named after you or specimens named after you, even if, because the museum itself may not have had the money to buy the collection. So those are ways you can help, I think.
Yeah, that's really amazing. And I don't really know anybody who wouldn't want a fossil named after them. That would be really cool.
Yeah.
Well, Paul, thank you so much for coming on to the show again. You really taught me a lot today. So thanks again.
Well, thank you very much for inviting me, and good luck.
Absolutely. That was so informative. Who knew that the field of paleontology was so complex? I love the idea that we can use the past in order to better understand the present. If you want to support paleontology, you should definitely check out the Paleontological Society and try to visit your local museums. Because I live in New Jersey, I love to visit the Museum of Natural History in New York City, but there are tons of other museums that you can visit as well. Thank you so much for coming on this adventure with me as we explored the world of prehistoric arthropods. You can find the sources that we used for this podcast and links to organizations that we reference at onwildlife.org. You can also email us with any questions at onwildlife.podcast@gmail.com. And you can follow us on Instagram at on_wildlife or on TikTok at onwildlife. Don't forget to tune in next Wednesday for another awesome episode. And that's On Wildlife.
You've been listening to On Wildlife with Alex Ray, brought to you every Wednesday.